Okay, so ceramics. The syllabus in personal and public transport says ceramics is an insulation material, which is really spark plugs and spark plug insulators, and heat insulation in vehicles. Laminating of glass, heat treatment of glass, as in, that's all it says, just how windows are used. We've spoken about beforehand when I was growing up in the 1970s in far west New South Wales, driving between Cobar and Bourke. We'd be driving along, and every time a semi-whip trailer went past, everybody in the front seat had every hand on the windscreen to stop it from shattering, because the windscreens in the 70s were not like today and laminated. They were like the side windows in the class, heat treated. Side windows in the car, heat treated. And when the rock hit the window, all of a sudden it shattered into little tiny cubes, and the driver couldn't see while they're doing 115 kilometres an hour. So at that point, that's a bit dangerous. They used to, here's the driver's side, we're looking at the front, there's the steering wheel, there's the driver. They used to just basically change that area of the windscreen slightly, so when it broke, it didn't break as badly as the rest, so you could still see through it and stop. Then you had to punch out the windscreen, knock it out with whatever you can find, and drive to the next town at 60 k's while you've got the wind blowing straight in the entire car. It's called safety glass, but in this case it wasn't really safe. Let's first up have a look at the structure-property relationship of ceramics. It is really simple. Ceramics, as you know, are brittle. Ceramics have got a set crystal structure. Positive, negative. That might be sodium, that might be chlorine. Over here, chlorine, over here, sodium, and so on. Chlorine, that's negative, that's positive. That's negative, that's positive. That's negative, that's positive, that's negative, that's positive. So ceramics are held together, ionic ceramics, by electrostatic attraction. Just the positive and the negative charges. If I, however, put a crack in there, at the atomic level, there's the crack. Now that distance is wide, there's no electrostatic attraction anymore and it falls apart. So if you can just put a tiny crack in a ceramic, separate the atoms, there is no force holding the atoms back together again. That is one of the reasons why ceramics are brittle. The slightest amount of atomic deformation means the atoms don't stick together. The other way, we've spoken often in metals about atoms moving sideways. So if I go from the standard structure, that was positive, that's negative, that's positive, that works. If I physically push that row of atoms down by a point, it's by 200 times 10 to the minus 12 of a metre. Milli, micro, nano, there. If I push that down by that many metres, that atom now is completely there. That becomes the negative atom that was sitting up there. This chlorine atom now sits there. So if I can move the atoms by that tiny amount, all of a sudden I've got negative and negative charge. What happens when you put two negative charges together?
Repulsion.
Repulsion, falls apart. Repulsion, repulsion. If you can move an atom by that many metres, it falls apart. That's why ceramics are brittle, for those two reasons. The window glass you have in the car is based on silicon oxide, which is also covalently bonded. Starts out life as a crystal. Crystalline structures are generally not transparent. Quartz is an exception. But it also melts at a really high temperature. To make glass form at room temperature, once again, all the scientific discoveries are an accident. They were taking sodium or potassium, potash it's called, potassium carbonate, from the West Indies back to England on a sailing ship. Of course, sailing ships take 3 weeks, 4 weeks, and they need fresh water. The sailing ship went past an island, the sailors got off, got the fresh water for the ship, and then went, oh, while we're here, we'll camp overnight. And they lit a fire, and they needed some bricks. They went onto the boat, got some potassium carbonate off the boat, set it on the sand, on the ocean shore, set a fire, and in the morning, they found glass. Literally, that is how glass was discovered. It is just sheer happenstance. And that was about the 1500s or so. And it's modified silicon oxide. Silicon oxide, I'll let you Google a picture, it is in your textbook, it's in Rochford. But silicon and oxygen works in a tetrahedron. It's basically a hexagonal bond, really tightly structured lattice, whereas silicon quartz. It's hexagonal structure, which is why quartz crystals are hexagonal, because the atomic structure is hexagonal. What they do here with the potassium goes inside that silicon, destroys the structure. So we've got silicon, oxygen, silicon, and then over here, potassium, potassium, and it basically destroys all the bonds, destroys the structure, makes glass completely amorphous. Amorphous, no structure, absolutely transparent. Glass is also brittle because the slightest misalignment in those bonds just means it shatters. There's a really high energy at the tip. So, we've looked at structure properties, we're sweet, we're done. Cool with that? Mm-hmm. Ionic ceramics are really easy to understand. It's just the electrostatic repulsion. Structure properties, tip. As I said, the silicon oxide structure being covalently bonded, it's a slightly different fracture mechanism, but understand that ceramics have a high Young's modulus. That's E equals stress on strain. Why? Because when you stretch them a little bit, there's a massive force trying to pull the atoms back to the right position. Young's have got a really high Young's modulus. Ceramics have a really high Young's modulus. Please feel free to look in your textbook while I'm explaining this. We've got as well, which page in Rochford is it? Somebody yell it out when you find it. So ceramics have got a high Young's modulus. They are brittle. They've got a low ductility. Strain to failure. Ductility is how far can you stretch something before it snaps. They've got a low strain to failure. They've got a high Young's modulus. And they are brittle. There are very few, if any, tough ceramics. The way they do toughen a ceramic used to be in the syllabus, it's not. It's got to do with stopping the stress at the crack tip with internal transformation, well and truly outside HSC. Mm-hmm. So, let's now concentrate quickly on insulation, structure properties. Heat transfers by vibration. Electricity transfers by electron transfer. At the atomic level, how does the energy get from this atom to that atom? Through the electrons. This electron starts vibrating with heat, which vibrates this electron. That electron then starts interfering with this one. And then it just moves through. Ceramics are really good insulators because they're not metal. Metal has got that sea of floating electrons that lets the heat transfer across really easily. That's the electricity transfer. The syllabus could be talking about heat insulation, could be talking about electrical insulation. Both are valid. It's the same mechanism. It's just electrons. For electricity transfer, they physically just swap and move. So if I put a positive charge there, all the electrons come across, and then of course you've got to have a negative feeding everything back in. Yeah? Have we found a page in the text?
150.
150?
Yeah.
Page 150 of Rochford. Okay.
Or 151.
151. Okay. So, how does it go thermally? This electron vibrates, goes to that one, goes to that one, goes to that one, off it goes. Ceramics don't have that. Ceramics are ionically bonded. An ionically bonded ceramic, there is no electron that's spare Because there's no electron that's spare, it cannot transfer electricity. It's an electrical insulator. Because there's no electron that's spare, heating this up takes a while. That entire atom's got to vibrate enough to get to this one. And it takes a lot longer for the heat to travel across. So insulation could be spark plugs, it could be thermal insulation inside an engine, something to stop the heat from getting, say, to the car bonnet or the occupants. Glass wool, the insulation wool, is just basically there to stop airflow, and the air becomes the insulator. Just gas, bubbles of gas molecules. The gas doesn't heat up as quickly as a solid. So that's how air insulation works. So, I'm going to tick off insulation, which is really another structure property relationship. The final two is window glass in cars. How does it work? As I said in the very early introduction, first one is safety glass, tempered glass. Glass is made like this. Coloured, which is broken glass, and recycled glass. Recycled glass is put back in a furnace. The early stage of this syllabus says talk about recyclability of materials. Glass is readily recycled and often recycled. You only need to put all the massive dollars into making it once, and then you can just melt it down, reform it really easily. So you have colour, you put in sand, you put in soda ash, which is the same as the potassium oxide, goes in a furnace. 2200 degrees C or thereabouts it melts at. Inside that furnace, 2200 degrees C, you need insulation on the inside of it, don't you? It's once again, it's silicon bricks. They slowly dissolve, and then when they dissolve too much, you put new silicon bricks in. Yeah? If you can get right so the outside's cold, then it just freezes automatically onto the silicon bricks. And then you never need to replace your furnace bricks. It's only when you make a mistake and you let the bricks get too thin, you've got to stop it, or over time. I don't know how long it takes for the chemicals to dissolve the bricks out. I've never worked in a glassworks. Worked in something similar, ceramic factories, but never a glassworks. So, and out the end comes molten glass. Old school until the 1940s, they used to get the glass out and roll it between two rollers. Just like rolling steel, you'd roll glass. If you look at all the old houses, you'll see lines in the windows. The lines in the windows are from the rollers. And then they found a nice, easy, cheaper way to do it. They just pour this molten glass out the furnace. It's running kind of like honey. So it's not running like water, it's running like honey. Onto a bath of molten tin, which melts at, I can't remember, 600-700, something like that. I used to work with tin, but never molten. But it melts at about that. And it floats and freezes. And at the other end, you have got glass that's absolutely optically smooth. Cheap and easy. All your modern windows are made using float glass method. Has anybody heard the word float glass? No? So I'm going to put that there. Float. Is it in the textbook? Page 150 thereabouts? Yeah, so page 151 of the text, we're talking about float glass. That's what it actually is. It's floating out on a bath of molten tin. Come to the other end, but think through your window glass. You tap it, it shatters. You tap it, it shatters. Glass has got a really low ductility. If you think about going back to civil structures and beams, if I bend that glass slightly here, this lower side is in tension, isn't it? Yeah? If there's the tiniest defect on the surface, the glass shatters. So that's why your window glass is brittle. Because it's naturally brittle, but if you have the tiniest defect, it shatters. Optical fibre, when we get to glass in telecommunications, they physically melt a rod of glass and they draw it out. Drawing, there's that term again. Making a wire. They physically get the molten glass and they draw it out. Any voids, any bubbles, any defects just get closed up and sealed up. So optical fibres are pretty well defect free. Every defect, the light travels down the optical fibre, hits the defect, bounces backwards. There's too many defects, your NBN doesn't work because the optical fibre just reflects everything back to the source. Make sense? So, glass shatters because of that. Too easy once again? So how they get around that? If you think about it, on top, it's cooling quickly. On the bottom, it's sitting on molten tin. Slower or quicker? Slower. We've got a differential cooling happening in that sheet of glass. Then when I come out here, this might be 200 degrees. That might be 20, let's pick a number out the back of the furnace, 20 degrees in the factory. When the glass cools, then it naturally wants to bend. The only thing that's stopping it is the fact it's rigid. So it's got internal stresses as it cools inside. Yeah? How do you get rid of them? Out the back of this furnace, I'll just keep the furnace going down here. Which language do you think that comes from?
Latin.
Latin almost, it's German. German. Leer. It's a leer. A leer. Okay, and what that means is it's a flame. Just heat it up from on top, heat it up from underneath. The glass gets to a point where it's soft and all the stresses inside relieve itself, and out it comes as being a standard glass sheet or a glass bottle. Annealing in a leer. What's annealing? Heat something up to allow stresses to remove, cool back down. It's in metal, it's exactly the same in glass. Same term, same meaning, different product. Glass bottles are blow moulded. We haven't covered it yet, but we're about to. They blow them out with cold air inside a cold mould, full of internal stresses. Then they've got to anneal them, or else the first time you put them in the supermarket shelf, the poor person putting them in, the bottle explodes in their face when they bump it on a shelf. Gets rid of that, yeah? So, that is how normal glass is made. If you're careful about this, if you heat it up and you take it out,
Followed by forced air cooling to cool the outside quicker than the centre.
when both sides are at, let's pick a number, I'm picking something out of the air here. Both sides are at 300 degrees, and the inside might be 600. As it's coming out of the furnace, back down here. If you're careful how you make tempered glass, your shower screens are tempered glass. They get this standard glass and anneal it.
Followed by forced air cooling to cool the outside quicker than the centre.
What happens? As that cools down, that shrinks a little bit. I'll draw the arrows in the right way. That bottom shrinks in the same amount. The top, the middle shrinks in further than the top and the bottom. Yeah? Mm-hmm. This is your windows. These are your car side windows, which is tempered glass. Okay. Car side windows, tempered glass. This is the tempering process. What happens now? At room temperature, I'll just get rid of my furnace, I don't need it anymore. What now happens at room temperature? That middle shrinks more than the two outsides. Because the middle has shrunk more than the two outsides. In here, that is now internally in tension. Because it shrunk more than the outside. And because that's in tension, that's got to be in compression. That's got to be in compression. Yeah?
Yeah.
And because that's in compression, now if I get a defect on the outside, let's go back to trying to bend this, I'll put it down underneath. There's the defect. That's got compression or a compressive force on it. It's pushing it closed. Correct? So to make it snap, I need to have a lot more force on that to bend it further, don't I? That's why your window glasses are safe. Window glass is one of the reasons it's called safety glass or tempered glass. because it takes a lot more force to shatter. The other reason is when it goes, there's the point it shatters, that spreads out, and then that internal stress releases everywhere all at once. And you just get lots of little cubes, like the side windows in the car parks, where you've seen side windows get broken. You've seen all the tiny little cubes of glass, about 6 millimetres square on the ground. That used to be a side window, that used to be a tempered glass window. Problem, why it's great for everything. Means when the window shatters, if you're driving along, once again, past experience, when you're driving down the freeway at 110 kilometres an hour with a truck straight behind you and the cockatoos fly in front of your car, it's like hitting a flying house brick. What happens to your car windscreen these days at 110 kilometres an hour?
No, it stays intact.
It physically bent the entire window in. Our laminated glass windows are window glass. It's different. It physically bent the window in, probably like that when I hit it. That outside formed little plates of razor sharp glass, probably about 500 or 600 of them. And then they explode through the car at around about whatever speed you hit the cockatoo at. That's not really safety, but that's extreme. They're not really designed to have that happen on a daily basis. What normally happens with this sort of window, when you hit a rock, is all of a sudden you're driving along at 100 kilometres an hour and your road turned invisible when the windscreen shattered. Have you seen the side windows at car when they've been broken? Do you reckon you could see through it? Not really. What happens if you're driving at 110 kilometres an hour?
Are you gonna die?
Oh, you've just got to hope you know where the road was when you stop. And that's literally what used to happen. There were lots of accidents due to broken windscreens. Simply because you can't slam on the anchors. You've just got to slow down as quick as you can without skidding. And then stop. Yeah? So, heat treated glass is good, but it had that problem with road and drivers, as in it's not suitable for front windscreens. Once again, go back to World War II. Every invention comes out of wartime or motor racing, with very few exceptions. They needed a way to have glass in aircraft that was not bulletproof because that's too heavy, but when the bullets hit it, the windows didn't shatter. One option was to put in an acrylic window, a plastic window, or a polycarbonate window, but then they scratch easily. And when you fly through a sandstorm, all of a sudden you can't see out the window anymore. Because abrasion resistance, abrasion resistance is important. So what they figured was, rather than doing this, because same thing, you don't want to be in a dogfight with people shooting at you in your aircraft and then have every window in your plane turn non-see-through. That's a bit of a problem if you've got opaque windscreens. Good luck, I think the ejector seat's somewhere, that's about your only option. Yeah, so they had to find a way. So what they did was, they just get 2 sheets of bog standard window glass and glue it together with a clear elastomer. It's called, you don't need to know it for the exam, butyric acid is the one you make in science that smells like baby vomit. If you're that lucky, that's what it smells like, it's rotten milk. So they made a polymer based on that stuff that is absolutely crystal clear and sticks to glass. You just get this elastomer with glass one side, glass the other side, stick them together. That's your front windscreen. They just slump it, heat it up, slump the shape onto a mould so it matches the shape of the car that it needs. Get 2 of them, stick them together. That's your windscreen. Now the advantage, when it breaks, it still breaks in the same pattern as a normal window. What actually happens, that elastomer sticks the crack together and stops it from going further. So if it cracks, instead of cracking here like a standard window and going all the way to the end, it stops it about here. Just look on here, please, mate. Stops there, and then the elastomer is physically holding the crack together. So what stops your car windscreen from breaking is this stuff that physically holds the crack tip together. Just like that is holding the crack tip together. All good?